Are you? Okay. Good, sorry about that. Normally I remember to do that. Okay, so as we do mass calculations, if we have 6 of these identical balls and each one weighs 1 kilogram or has a mass of 1 kilogram, then the total mass would be 6 kilograms, okay? Makes sense, right? That's assuming they all have the same mass. But suppose we said the total mass was, oh man, 60 kilograms, right? Okay. So if the total mass for 60 kilograms, we could go reverse of that, right? We could figure out how many there are, right? And so what we would do, or what we could do, is we could say that the total mass is 60 kilograms, and it's 1 ball for every 1 kilogram, right? And so this is what we call dimensional analysis, the idea that you're using units to help you kind of go through the calculation. Kilograms divided by kilograms is 1, right? A kilogram divided by a kilogram, it's the same, so it's 1, right? So that would give us the number of balls, and that would just tell us there's 60 balls. Now that's an obvious answer, right? If each one weighs 1 kilogram and the total is 60 kilograms, then you got 60 balls, right? But that's essentially what we do when it comes to atoms and molecules, interestingly enough. We just weigh the whole thing. We know how much each one weighs, so that allows us through this calculation to figure out how many there are. It's kind of interesting, right? So one aspect of this is the idea is that atoms and molecules have mass, right? Atoms have mass. We know that that's the case. And we have that in what's called the periodic table, right? The periodic table talks a little or shows us a little bit about atoms. It's actually the periodic table of elements, right? Or the Mendeleev table. Turns out there's roughly 92 elements in nature, okay? And another 25 or so that have been produced in laboratories that are just so unstable that you don't really find them in nature, but they can be produced in laboratory. But in nature, there's around 92 of these elements, and they have names, right? So hydrogen we've all heard of. Helium we've heard of. Most of the sun is hydrogen and helium. It's roughly 80% hydrogen and 20% helium with some trace amounts of other elements. Carbon, of course, for those of you who are biology majors, carbon and nitrogen are important elements in biology. Then we've got these, nutrients like calcium, which is a metal, magnesium, which is a metal. These are the elements that we have discovered over, humanity has discovered over the years, right? And since there's so many of them, it becomes useful to classify them and to categorize them and to number them and all of that. So they're numbered. Initially, they were numbered by mass. So the lightest one had the smallest number and the heaviest one had the largest number. But over time, it was discovered that the pattern we observe is not really a mass pattern. That's just sort of a coincidence. It's a byproduct of the fact that the structure of the atom, right? The atom has structure, and that internal structure gives rise to all these patterns that we observe in nature. So let's talk a little bit about what's called the atomic number. Which is simply the number of protons in the atom, right? Of one of these elements. Right? Each of these elements has some atomic number, which means it has some number of protons. And it turns out that's actually that's probably the most important pattern that we observe, is that the number of protons determines not just what an element is, whether it's hydrogen or oxygen, but also like how they interact with each other. And so we'll talk a little bit more about that later on, but it's an interesting aspect of it. So what we do then is we classify these and we number them. So the atomic number, sometimes it goes up here, up above the symbol of the element. So this would be the symbol for hydrogen, and hydrogen is the first element in the periodic table, right? It's the lightest element. It has a mass. And to 3 significant figures, it has a mass of 1.01. So that's what we're really going to be using in this chapter is, and throughout the course, is that number down at the bottom, which is called the atomic mass. Okay. This up here is the atomic number. So the atomic number determines what element it is and how it behaves. The atomic mass is just how much it weighs, right? But it turns out that that's pretty useful to know that. So the second one, which is you always, generally you see it all the way over here on the right, because we'll get into the chemistry of this. And that's helium, right? So those are the first 2 elements in the periodic table. And it hasn't been known for that long. That's an E, by the way. Really only less than 100 years that what powers the sun and what powers stars in general is a process which we often call as burning, but it's not burning in the sense that we are used to, like you burn a match or you burn wood or fuel. It's a nuclear burning where these hydrogen atoms are thrown so close to each other through gravity, through enormous gravitational forces, that they're forced to fuse together into a helium atom. And it's a relatively complicated process, but it hasn't been understood for that long that this is what powers the sun and this is what powers stars. Hydrogen atoms are forced together. So those the 2 protons actually, so each hydrogen has 1 proton. So if you take 2 hydrogens and you put them together, you now have 2 protons and now you have a helium atom, right? It's more complicated than that. But essentially, in its essence, that's what happens. Those 2 atoms are not wanting to fuse together. It takes enormous gravitational force to do that. In fact, humans have been trying to mimic this in very sophisticated laboratories and very expensive laboratories for, I want to say, 60 years anyways. And with very limited success. It's still not successful. They still really can't get this to work. They're trying to create artificial stars in laboratories so that they can generate lots of energy. Because one thing we know about the sun, is that when that process occurs, when those 2 hydrogen atoms fuse into helium, it releases a lot of energy, right? Sunlight, right? Radiation that would kill us, would fry us if we were closer to the sun. Radiation that would kill us if we were on Mars, because the atmosphere of Mars isn't that great, as well as there's no magnetic field on Mars. The magnetic field of the Earth protects us by redirecting these rays to the poles, to the South and North Pole. So enormous amounts of energy can be released through this process. But so far, it's such a difficult thing to do. It hasn't happened on the Earth. So most of the universe is, at least most of the traditional matter, is hydrogen and helium atoms, right? Most of the stars are made out of hydrogen and helium. But we do have heavier elements, right? So for example, we have lithium. And lithium is important in terms of battery technology, right? When I started teaching, which is now a while ago, when we talked about lithium, the main thing about lithium was that it was used as a medication, lithium carbonate, for bipolar disorder. But now lithium is a strategic mineral. It's a strategic element that countries are sort of fighting over now because of its value in high energy density batteries, right? And there's a scarce amount of it on the Earth's surface. So now that's the main application of lithium. So notice lithium is heavier than helium, and it is essentially produced by a similar process. You start taking things like helium, you take a helium atom and you fuse another hydrogen atom into it. Again, it's more complicated in terms of protons and in terms of neutrons. but you end up with this pretty complicated process where you get now a fusion that leads to lithium, and that releases energy too. So in a star, not only is hydrogen being converted into helium, but helium is then being converted into lithium. And it kind of continues on. It continues into the next one, which is beryllium. And then it continues on into the next one, which is boron, and then into carbon, and then into nitrogen, and then into oxygen, and then into fluorine, and then into neon, which is the next noble gas, right? So this process just keeps going on and on and on and on till you get all the way up to 26, which is iron. And suddenly iron is a really stable element from a nuclear perspective. It does not easily get converted into other things. But we know that we have elements in nature all the way up to 92, which is uranium. So scientists were wondering, well, if iron is so stable and it's difficult to fuse it into other elements, how do you get the elements that are heavier in that, which would include things like gold, right? So gold, which is element number 79, that's way higher than 26. How does gold get formed? And we have gold on the earth. And so the result, the answer to that question is very interesting. It turns out that in order to get iron to fuse with other elements, you need something more powerful than a star. And so what's more powerful than a star is an exploding star. So when a star explodes, which is called a supernova, there is enough energy in that explosion to fuse these heavier elements like iron and to convert them into the heaviest of the elements in nature, things like gold and uranium. And so then you start to go through the reasoning. If there is gold and uranium on the earth, then where did it come from? It had to come from some sort of explosion that occurred a long time ago before the Earth's solar system was even created. And so that tells us that, in fact, our own star is at least a second generation star, probably much older than that even. The universe is close to 14 billion years old, and our own star is only 4.5 billion years old. So previous generations of stars would undergo these processes. Some of them, a small percentage of them, would blow up. And when they would blow up, that would lead to the formation of new solar systems, including our own, which would now have these heavier elements like gold and uranium. Okay, so that's a little bit of background on the periodic table. Of course, each of these elements has mass, right? So I'm not putting them all in here, but carbon is 12.01, nitrogen's 14.01, oxygen is 16.00. And they get higher, the mass, this atomic mass gets heavier or higher as you move along. Every time you add a proton, you add a little more mass. Every time you add a neutron, you add a little more mass. So since these elements, as we move across, have more protons and more neutrons, they are, as a result, heavier elements. Okay, so what we're going to do is we're going to use these atomic masses to do calculations. So like I said, even though what an element is given by its atomic number, it's actually the atomic mass that we use to do calculations, at least to do mass calculations. Okay, so that leads us into something called Avogadro's number. And there are different symbols for Avogadro's number. Typically, it's a capital N, uppercase, but often it has an A next to it as a subscript. So N sub A would be Avogadro's number. And I'm not going to go through the whole history of where it came from and how people figured it out and why they figured it out, but it is useful for us in terms of counting. And the first thing I want to bring to your attention is how large the number is, right? It's a huge number. I'm only writing it out to 4 significant digits. It's known to 9. And now it's defined as a specific value. 4 significant digits in this one right here. 6.022 times 10 to the 23rd. And you can think of it analogously, sort of like the way we use a dozen, right? A dozen is 12. Why do we use a dozen? We use a dozen because it's easier to count larger numbers, right? So it's easier to say, look, I've got 5 dozen eggs than it is to say I've got 60 eggs, right? We count in terms of dozens. In English, we used to have other ones like gross people would use. Score is like 20. So there were other units of counting. In generally, the dozen is the only one that we use now. So Avogadro's number is kind of useful for counting large numbers of objects. In this case, we're going to talk about atoms, molecules, photons, things like that, protons, neutrons, electrons. So it's a very large number, and it's a very large number because there's large numbers of atoms. In your body, there's huge numbers of atoms, right? There's more than a mole. There's like, I don't know, it's like 20 mole or something like that of atoms in your body. Maybe it's even more than that. But it's a very useful number because of its huge value, okay? So for us, we're gonna call this 1 mole. So just like we would say a dozen is 12 objects, we would say that a mole is 6.022 times 10 to the 23rd objects, okay? So that's how many objects is in a mole. So dozen, mole, a dozen is 12, a mole is this large number here, okay? So now imagine if I said, look, suppose I said I've got 10 moles of hydrogen atoms. Okay, how many atoms do you have? Well, now you've got this little conversion factor here, right? So you would say you have 10 moles. By the way, when we abbreviate mole, it's usually abbreviated MOL, okay? And then you would say in 1 mole, there's this Avogadro's number. So 6.022 times 10 to the 23rd per 1 mole. See how I wrote this as a conversion factor? So here's our identity, our equality, if you want to call it that. This is written as a conversion factor. And again, it's the whole idea of dimensional analysis is that just like, if I have 2/2, that's equal to 1, you can do the same thing with units, right? Or you can do it with variables, right? Like if I said x divided by x is 1, right? That's not true if x is equal to 0, but in any other case, it should be true. Same is true with units. I can say a mole over a mole is equal to 1, or a meter divided by a meter is 1. Or I could say a meter squared over a meter. We can cancel one of the meters on the top and the bottom, right? And then that leaves us with meters. So you can do this whole kind of algebraic analysis with units, and that's kind of cool. So the idea here then would be that mole divided by mole is 1, and then that's just going to give us a number. Of course, if we're taking this number and we're multiplying it by 10, that would give us this number, right? If you multiply 10 to the 23rd by 10, you just get 10 to the 24. You're just adding an extra 0 at the end, right? So I didn't put any units in here. I mean, you could be explicit about it and say this is how many hydrogen atoms we have. But, that's kind of optional, all right? So that's the usefulness of the mole, is that it's this very large number, so it just gives us a way to count things. Instead of saying, hey, look, I've got 6.022 times 10 to the 24 hydrogen atoms. That's a mouthful, right? You just say, I've got 10 moles of hydrogen. And that means something if you understand what the mole is. The mole is this very large number. So just like I would say, hey, I've got 10 dozen eggs, that would in your mind mean, 10 dozen, that means I've got 120 eggs, right? Because it's 12 times 10. So same thing here. So we can count things. And we can go backwards as well. We could take the number of atoms and figure out how many moles that is, and then go from there, right? So that's essentially what we're going to look at the beginning here, is this idea of using Avogadro's number, right? So that's Avogadro's number, and using the mole. it turns out the mole is really the go-to unit for, you know, quantifying how much stuff you have. There's different ways to quantify, right? So like one is mass. I could say, look, I've got 150 grams of water here, okay? Or I could talk about volume and I could say I have 150 milliliters of water, right? So those are two different ways. But it turns out there's reasons why volume is not necessarily a good measure in some cases, and there's reasons that mass is not as well. So for that reason, typically the mole is the go-to. The mole is independent of temperature, it's independent of pressure. The mole is just, hey, that's how much you have. So if I say I have 1 mole, that tells me I have 6.022 times 10 to the 23rd of whatever that object is. Okay, so let's take a look. Let's go back. Let's go back to that problem and take a look at that Alex problem. So I'm going to stop share there and then bring that one back up so you can take a look at it. Okay, there we go. So keep in mind when you're doing the Alex problems, they're going to give you ones that are relatively similar to each other, but you got to get 3. You got to get 3 of them right. Okay, you are able to look at the explanation. So if you're really kind of, you know, you're trying to do this problem and you're struggling through it, sometimes it's useful to look at the explanation and then they'll give you another one to try, right? You don't get penalized in the sense. Oh, by the way, you can get these problems wrong multiple times and you get penalized for it, meaning it's not going to lower your grade, right? So it's just, you eventually got to get it right 3 times. And if you get it right 3 times, then you solve that problem and you're done with it. You can move on to the next one, but you don't get penalized if you get it wrong, okay, in terms of your grade. So this one says using the Avogadro number, or I call it Avogadro's number. And the question is, a brick has a mass of 4.0 kilograms, and the Earth has a mass of 6.0 times 10 to the 27 grams, G for grams. So these are masses. Notice the brick is in kilograms and the Earth is in grams, right? Physicists would put the mass of the Earth in kilograms too, but Alex will sometimes do this just to make you do an extra step. So use this information to answer the questions below. Be sure your answers have the correct number of significant digits, right? What is the mass of a mole of bricks? Okay, easy enough. We'll go ahead and round it to 2 significant digits. So the reason it's 2, the reason they want you to do it in 2 is if you take a look at this number here, the bricks, it's 2 significant digits there. So if your measurement has 2 significant digits, your answer should have 2 significant digits. And then how many moles of bricks have a mass equal to the mass of the Earth? Okay, we'll go through that and round it to 2 significant digits. Again, notice how this number here has 2 significant digits, as does this one. So they're being kind of consistent. They're giving 2 significant, I call them figures, significant figures, but you can call them figures or digits, whatever. They all have 2, so your answer should have 2 there. Okay, so let's take a look. I'm going to go ahead and work on this one for you. Okay, so I'm going to go ahead and write these numbers down. So the brick is 4.0 kilograms. That's about 9 pounds, 8.8 pounds or so. And the Earth is 6.0 times 10 to the 27 grams. And then here's our question. We want to know the mass of 1 mole of bricks. Okay, so let's take a look at that. So here's what we can do. We can say that 1 mole is 6.022 times 10 to the 23rd objects, right? It could be any object. It could be planets, it could be stars, or it could be bricks, right? And so that's how many bricks are in 1 mole. Let me actually bring this up here because I'm going to have to use it. There we go. Okay, so this is relatively simple, right? What you could do is you could say, look, here's the mass of 1 brick, 4 kilograms per 1 brick. I'll write it this way. That's how much 1 brick weighs. And then we want to multiply that by 6.022 times 10 to the 23rd bricks. Now, it is useful to write Avogadro's number this way, okay? Because the Avogadro number is how much is in 1 mole. So I typically like to write it this way. You write the Avogadro number, this right here, and then you write the mole on the bottom in the denominator there, right? And the logic behind that is, you know, this is equal to that. So you can write a ratio. Let me do this as an aside. You can write the ratio as just taking 1 divided by the other side. 1 mole over 6.022 times 10 to the 23rd. Or you can write it the reverse, 6.022 times 10 to the 23rd per 1 mole. Each of these is equal to 1. Why? Because if you do the following, if I take this equation right here and I divide both sides by mole, a mole over a mole is 1. So you have 1 on the left side and you have mole down here. If you divided both sides by the number, then you'd have a mole over the number, but this side over here would be equal to 1 as well, because this number divided by itself was 1. So this right here is 1, and this one is 1 here. So I'd use this one because that's going to tell us what the mass is for a mole, okay? So now, if you want, you can cancel the bricks, that's fine. And then you just multiply them. So 4 times 6.022, and you get 24.088 times 10 to the 23, and then you're gonna have mole down here per 1 mole, okay? Now, this is not in scientific notation, okay, right? That's not in scientific notation because scientific notation is a number between 1 and 10 times 10 to the x, where x is a whole number. So I'm just gonna move this to the left 1, okay? And that's gonna give me 2.4088 times 10. Now, when you move it to the left, this increases. I remember it as lip. Left is positive. So if you move the decimal point to the left, the exponent becomes more positive by 1 in this case. So now you have a 24. And again, that's per 1 mole. Okay. Now, what about the significant digits? It said round it to 2, right? So here's the most significant. So we're going to keep that. Here's the second most. We're going to keep that. Everything else, we just truncate it. We get rid of it. So that would be 2.4 times 10 to the 24. And that's per mole. Okay. So then the answer to our first part of this would be, it says, what is the mass of 1 mole of bricks? Let's see. Oh, I forgot the units. I'm sorry. My apologies. I forgot the units here. So this was kilograms, right? This is right here. I'm sorry. I completely forgot that. Okay. So there's our answer in kilograms. But now there's an issue, which is in the ALEX question, they wanted us to give the answer in grams. They didn't want it in kilograms, they want it in grams. So we have to do one more step, which is a conversion, okay? So what I'm gonna do is I'm gonna take my answer here. (2.4) times 10 to the 24 kilograms per mole. And I'm going to convert it to grams. It's just because they wanted it in grams. They didn't want it in kilograms. Okay. So how do we do the conversion? Kilo is K, and it's equal to 1,000, or in exponential notation, 10 to the 3. So here's how I'll do it. Kilo is 1,000. So actually, I could just do it more simply than doing the full conversion. I'll show you what this way. So 2.4 times 10 to the 24. Kilo is 10 to the 3. So you write it as 10 to the 3 times 10 to the 3 is kilo, and then grams. Okay, so kilo is 10 to the 3. So 10 to the 3 grams is a kilogram. Now, if you're multiplying powers of 10, you just add the exponents. That's all you got to do is add the exponents. So 24 plus 3 is 27. So that's going to give us 2.4 times 10 to the 27 grams. And that, again, that's per mole. But they just want you to give them the answer in grams. And that's 2 significant digits, 2.4 times 10 to the 27. Okay. All right, that's a big number, right? That's how much 1 mole of bricks would weigh. Of course, it's a lot of bricks, right? If you stacked a mole of bricks, it probably would go from here to the next galaxy. That's how big it would be, okay? So now the second part of the question, so there we go. So let me stop this video here and bring it back up. Oops, there we go. So the second part is how many moles of bricks are equal to the mass of the Earth. Okay, so we know the mass of 1 mole. The mass of 1 mole of bricks is 2.4 times 10 to the 27 grams. Same units as the mass of the Earth. The Earth is in grams, right? So we already have the bricks in grams, 10 to the 27 grams. It's pretty close, right? If you think about it, if I compared 10 to the 27 to 10 to the 27, they're equal to each other. So they're actually, it's roughly speaking, it looks like it's a little more than 2 moles. So let's take a look. Okay, so the mass of 1 mole of bricks is equal to 2.4 times 10 to the 27 grams. The mass of the Earth is 6.0 times 10 to the 27 grams. Okay, so here's what we can do. Okay, I'm going to try it this way. What I'm going to do is I'm going to say, let's reason through it, then I'll show you the formal calculation. Imagine I had 2 moles of bricks, right? Well, that would be just 2 times 2.4 times 27 grams, 10 to the 27 grams, right? So that would be 4.8 times 10 to the 27 grams. That's if you had 2 moles, right? Because it should be 2 times 2.4. Suppose I had 3 moles. That would just be 3 times 2.4. And that would be what, 7.2? So what we know now is that the Earth is in between those 2 numbers, right? 6.0 times 10 to the 27 is right in between. It's right in between those 2 numbers. So we know it's going to be between 2 moles and 3 moles. Okay, so what I'll do is I'll just say, look, I've got 6.0 times 10 to the 27 grams. That's for the Earth. I'll write that in parentheses. And then it's 1 mole of bricks per 2.4 times 10 to the 27 grams of bricks. So see what I did here? I took this equation here, this equality, and I wrote it as a ratio. And what I did logically in my own mind was I said, look, I want to know how many moles it is. So I want to have the moles on the top so that the grams cancel and I have moles. So that's why I knew not to do it the other way. I knew not to do it this way. Because look what would happen if you did it this way. You would have grams, which is the mass of the Earth, times grams, which is the mass of the bricks, divided by moles. And your units would be grams times grams over moles. Well, that's grams squared over moles, but that's not what we're looking for. We're looking at how many moles there are. So by putting the mole in the top, now the grams cancel and you got your moles. So it's really just 60 divided by 24. What is that? 60 over 24? 2.5, right? It was right actually in between. So that's 2.5 moles of bricks, which is interesting because, to me anyways, this is interesting because what that tells you is that if you took the entire mass of the earth and somehow converted it into bricks, and you can maybe imagine some advanced civilization that has that ability to just convert matter, and make a bunch of bricks out of a planet, you would end up with 2.5 moles of bricks. Okay. Again, that's a lot, right? And it would be enormous length if you stack them edge on edge or anything like that as a pile. But that's essentially how many bricks you could get out of the earth. The earth is, primarily rock, right? There's iron and nickel at the center, and there's water on the surface, but it's mainly rock. So in theory, you could, turn the earth into a bunch of bricks, and you'd have 2.5 moles of bricks. Okay. So that's our two-parted question there. And that's kind of just really getting you into the idea of Avogadro's number. Let me close that one, sorry. And what I want to do, I do want to show you just so that you can see it, that when you do these problems, there is an explanation available, right? So notice that they're using a much larger value. Actually, they use this value of Avogadro, 6.02214. So they added a couple of extra sig figs. But again, you get, the mass is 2.4 times 10 to the 27 grams. Okay. So see, the one kind of, I would say it's a little bit of a weakness about about Alex. They don't show every little detail like I did. So for example, they have your 2.4 times 10 to the 24 kilograms. They just immediately put that to 10 to the 27 grams, right? But I went through that a kilogram is 1,000 grams. So that's that conversion. And then they did this. They didn't really show you the dimensional analysis. They just said, take the mass of the earth and divide that by the mass of the bricks, and you get 2.5 moles. Okay. So there is explanation there. And then, as I said, you got to do 3 of these to move on to the next topic. Okay. So let me see if we can work on another one, another problem. Here we go. Let me see if we can do this one. I just want to pick one. Here we go. Let's try this one. Okay, next type of problem. This is getting a little bit more about the periodic table now. So this says calculating and using the molar mass of the elements, okay? In this problem, it says that a chemist weighed out 101 grams of iron, calculate the number of moles of iron she weighed out, and in this case, you want your answer to have 3 significant digits, okay? So now we're getting into this issue of the periodic table and how we use what's called the atomic mass, okay? And again, you see this term here, moles, right? So notice you have moles of a substance. In this case, it's iron, which is element number 26 in the periodic table. And then you're given a mass, right? So this is 101 grams of iron. Sorry, it's not highlighting it for me for some reason, the formatting. Okay, so 101 grams of iron. So this one has to do with iron. So let's go through this problem because this is a very traditional and useful type of problem that you'll use in the laboratory. You'll use it throughout this course. You'll use it in the next course if you take more chemistry. Very common type of problem, okay? So let's take a look at it. Okay, so what we're told in this problem is that we weighed out 101 grams. Notice they put the decimal at the end there. This has become kind of common that even if the number you're measuring out doesn't have anything after the decimal point, you still write the decimal point after it. So 101 point G of iron. Okay. And then we want to calculate number of moles. Okay, of iron, right? Okay, it's very straightforward. Here's what you do. You look up, and I'm going to make it in a little box just to make it look like it looks in the periodic table. Iron is 26. Okay, by the way, Alex has a periodic table. So if you're, you know, when you go through the tutorial, the tutorial will show you how to access the periodic table and how to actually click on the element so that you can use its atomic mass in the calculator on Alex. So feel free to do that. Or just, but use the atomic masses that Alex gives. Use its periodic table, because what happens is the number of significant figures or significant digits in a periodic table depends on which table you're using. So someone like me, I tend to use 2 digits after the decimal point because most textbooks, that's what they use. But some, including Alex, have more. So just make sure you're using their values, because otherwise what happens is you'll be off a little bit and Alex will kind of bother you about that. Okay.
What are the units of the, I'm sorry to interrupt, what are the units of the atomic mass?
Very good. So let's talk about it. So here's the units we're going to use. So I'm going to write it this way. I'm going to put the units in here. It's grams divided by moles. And I'm going to abbreviate the mole. So I'm abbreviating mass, right? So this is grams. Okay, so this is a measure of mass. And then this is moles, which is a measure of the amount, right? Of course, it's 6.022 times 10 to the 23rd atoms. Right, that's what a mole is. So notice that you're really hitting it sharply right there, Sophia. The units of this mass is grams divided by moles. And that is a bit of an issue for some scientists, because engineers and physicists tend to use kilograms. So if you look in a physics book, it's 50-50 in physics. Some physics books, the periodic table will be in kilograms per mole. Some of them will be in grams per mole, but chemists, we put them in grams per mole. The gram is kind of an older unit, and mass is typically in kilograms, but in chemistry, we put it in grams. So it's grams per mole, okay? So those are the units. So what does that mean? Conceptually, what it means is that if you have a block of iron and it weighs, so, you know, let's just draw a little block of iron, right? If it weighs 55.85 grams, what that tells you is you have 1 mole of iron. Now, what's cool about this is that if you go into a laboratory, you can weigh 55 grams very easily. 55 grams is not that much mass. So it's, you know, it's a little pile about this big. Actually it's about, if it were a cube, it'd be about that big, okay? So that would weigh about 55, 56 grams. And so that's how much you now know, based on weighing something, how many moles you have. And of course, a mole is equal to the number of atoms. So yeah, so the units are grams per mole. So we can write it in 2 ways, or 2 other ways. We can write it like this: 55.85 grams of iron, Fe for iron, right, ferrum, is equal to 1 mole of iron. Okay? And so now we can use that in a conversion factor. We could write the grams divided by the moles or the moles divided by the grams. So take a look at what happens. In this problem, they give us the number of grams. So I'm going to take what's given. 101 grams of iron. And again, we're using symbols, right? So we're writing G for grams, Fe for iron, right? You could write it out, IRON, if you wanted to. Okay. Now we want to find the number of moles. So this is how we use the dimensional analysis. What we do is we say, okay, this is the unit we're starting with, but this is the unit we want. And we're going to use this as a conversion factor here. Okay. So what I'm going to do is I'm going to multiply this by, which one do we want? We want the mole. So I'm going to put the mole on top in the numerator, and I'm going to put the mass in the denominator. Okay, and take a look at what happens. The grams cancel. Grams over grams is 1. And the only unit left is mole. And so that's why we use this dimensional analysis throughout chemistry and physics, is because it's very useful in terms of directing us. Do you multiply by 55.85 or do you divide by 55.85? You use the dimensional analysis to tell you which one goes in the top and which one goes in the bottom so that you can cancel out units. And if you get the right units, right, number of moles, well, this is going to be moles. That tells you you're probably right. It doesn't tell you exactly, you can't be sure, but it tells you there's a chance you got this calculation right. So 101, and you're going to divide that by 55.85, and you're going to get, now in this one, they said to do it to 3 sig figs. So 1.8, let me write it out just to go over it. If we want 3, and the reason they wanted it in 3 is because this one has 3. So here's the first one. Here's the second one. Here's the third one, right? The 0 is the third digit, but the number that comes after it is 5 or greater. So if a number coming after it is 5 or greater, you round it, right? Round up, right? 8 is greater than 5, so it gets rounded up. So you get 1.81. And that would be moles of iron, right? And there you go, 1.81 moles. So if you have 101 grams of iron, that's how many moles you have. A little bit under 2 moles of iron, right? Okay, that's the idea. I'm sorry, excuse me. Let me show you one more and then we'll wrap it up.
Hello, Professor.
Yeah.
Can you hear me?
Yeah, go ahead.
Okay, so for these types of problems, wouldn't it be easier to just go to the periodic table, look at the atomic mass, and then just divide like directly? Like if it was on an exam.
But here's the question. Suppose I say you have 2.5 moles of iron. How many grams is that? What's the mass of it? Would you divide it?
So you're asking if you start off with grams and then you're asking about the moles?
If we start off with moles and we want to go to grams, now what do you do?
My intuition says you just do the reverse, but I'm not sure how that would work.
Yeah, that's good. You have good intuition, right? So here's what happens. It depends. And if you're using intuition, intuition works sometimes, but it doesn't work very universally, right? So what happens is intuition, it might be where you might get either right answer 70% of the time, but 30% not, or maybe you have better intuition, you might get it right 80% of the time. But if you use a method, right? A method in theory should work 98% of the time anyways, right? Maybe it doesn't work 100% of the time, but it works 98% of the time. So it's just an issue. Do you want it to work 75% of the time, 80% of the time, or 98% of the time? The other issue is that later on in the course, you start doing problems that have more units in them. So you might have to do multiply by this one, divide by that one, or divide by that one, and then, divide by this one and then multiply by that one. So, right. So you have 3 numbers instead of 2, or 4 numbers instead of 2, or 5 numbers instead of 2. So what you want to do is you want to develop a system that works for you. So if you trust your intuition, that's perfectly fine. That's fine. But I generally don't trust my intuition when it comes to calculations until I've done that specific calculation so many times that I'm confident I can trust my intuition. Okay, let's see here. I want to use one. that goes the other way. Funny thing here. Kilograms, grams. Okay, let's try this one. This will be the last one. We're out of time. So this one says calculating and using the molar mass of elements. So a chemist determined by measurement that 0.0100 moles of tin participated in a chemical reaction. So we want to calculate the mass, right? So in this case, we're given the number of moles of tin. And we want to figure out how many grams it is, okay? All right, so let's try this one. All right, 0.0100 moles of tin. Okay, by the way, the symbol for tin is SN. And then we want to find out what the mass is. There's different ways to word this, but they want to find the mass. What is the mass of tin? Okay, so tin. So we looked that up in the periodic table. Tin, which is what I was just busily doing there. Tin is element number 50. And the atomic mass or the molar mass is 118.71. Okay, so again, that's the number we're going to use. So we can either call that the atomic mass, which has the units of AMU, or we can call it the molar mass, which is grams over moles. And in these calculations, we're using the molar mass. So it'll be grams per mole. Okay. So what I'll do again is I'll say, look, here's our conversion factor, 118.71 grams, 71 grams of tin is equal to 1 mole of tin. Okay, then I'm going to take what's given, the measurement, and then we just need to decide which one we're going to multiply or divide, right? So we want to get rid of the mole, so we want the mole down here, right? Because moles over moles cancel. So that means this one's got to go on the top, right? And then that'll give us grams, right? Moles times grams over moles, that's definitely in grams. And there you go. So it's 118, or let me write out 0.0. Well, actually, this is easy enough to do in your head, right? If you're multiplying by 0.01, all you got to do is move the decimal point over 2 places. So 1.1871 grams of tin. That's a lot of digits, right? In the question, they said to do it to 3. So 1, 2, 3. The number that comes after the 8 is 5 or greater, so we round it up. So that 8 becomes a 9. So 1.19 grams of tin. And there you go. Okay. So that kind of makes sense conceptually, right? Because if you had 1 mole, it would weigh 118.7. If you had 1/10 of a mole, it would weigh 11.871. And if you had 100th of a mole, it would weigh 1.1871. And that's exactly what we got. It's just we're rounding it off a little bit. Okay. Let's see here. Okay, great. Yeah, gallium, exactly, right. So gallium, you think about gallium, you gotta look up, gallium's not a common one where you, like, when you go through problems, carbon, you'll remember it's 12.01, nitrogen, you'll remember it's 14.01, but gallium is one of those ones where, you gotta look it up and see what its atomic mass is. What is gallium, actually? Gallium is number 31, named after France, by the way, Gaul, and its molar mass is 69.72, right? So that one's in there. Okay, awesome. So we only got a chance to get through a couple of different types of problems. Generally, for chapter 3, I can do 3 or 4 types of problems, but we got through 2 of them. We got a start on it. So again, if you want to kind of go ahead and do more of chapter 3, you can look at the older lectures from the summer and the spring on YouTube. But on Tuesday, we will work through probably, let me see, take a look here. We'll probably go through actually like 6 different types of problems on chapter 3, and then Wednesday we'll do another 5 or so, and then we'll work through this chapter. Chapter 3, in terms of the number of ALEKS problems, is the longest one. It has 22 problems because some of them are really kind of short, quick little, like this one that we just did right here with 10 is a quick little calculation. So there's kind of a lot of them. The later chapters are a little bit smaller. Instead of having 22, there's like 15 for some of them, 14, 18 for other ones, okay? All right, so reach out to me if you have questions. I do Zoom office hours. Just kind of get in touch with me and we'll work out a time that works for you and me. And have a great day and have a great start to the semester. Again, for the laboratory, I'm gonna go ahead and post a video about the laboratory to each of your sections. But those of you that are actually in person on Monday, it's relatively straightforward. Come into class on Monday and they're going to give you a whole kind of intro into how we do the laboratories on campus. So have a great day.
Is it all right to reach out to you by phone right now about the ALEKS situation? I just have one of their supervisors that's supposed to be giving